morning friends. Up to 13.7 numerical of exercise we discuss, right? Today the 13.8 depends on to find out the time for decay, right? Now 13.8 is that the normal activity of living carbon containing matter is found to about 15 decays per minute for every gram of carbon. This activity arises from the small proportion of radioactive carbon C614 present with the stable carbon isotope C612. When the organism is dead, its interaction with the atmosphere ceases and its activity begins to grow. From the normal half-life 5730 year, half-life is given. Initial activity is given 15 decays per minute. So 5730 year is the half-life of carbon C614. Right. The age of the specimen can be approximately estimated. We have to find out the time for the age of the specimen made from the carbon. Now, this is the principle of carbon C614 dating used in archaeology. Suppose a specimen from Mohenjo-daro gives an activity of 9 decay per minute per gram of carbon. Estimate the approximate age of the Indus Valley civilization. In archaeology, how we find out the time given specimen or whatever the obtained in archaeology is how much old. For that purpose, this type of the calculation is done. Okay. Now, the normal activity of the carbon containing in matter is given 15 decay per minute. Therefore, the decay rate of carbon containing in matter, that is our initial activity. Therefore, we can write decay rate of carbon containing in matter there is our R0. R0 is equal to 15 decay per minute. And decay rate of the specimen taken from the Mohenjo-daro and for specimen from Mohenjo-daro, decay rate is R is given as 9 decay per minute. 9 decay per minute. And half-life is given and tau half is given as the 5730 year. Now we know that the initial activity R0 is equal to lambda n0 and activity in any time R is lambda n. Taking the ratio of these two activity, R upon R0 is equal to n upon n0. But from exponential law of radioactive decay, n is equal to n0 e raised to minus lambda t upon this n0. n0 cancel. Therefore, ratio of the at present activity to the initial activity is equal to e raised to minus lambda t. Here we have to find out this. Therefore, taking a length on both sides, or in other words, first we have done it this way. R is already known 9, R0 15. Therefore, we can write E raised to lambda t is equal to 15 by 9 is equal to 5 by 3. Now our interest to find out the t. Therefore, taking ln on both sides. Therefore, lambda t ln basic is equal to ln pi by 3. This value is 1. Therefore, lambda t is equal to ln convert into the log. Therefore, first let out what is the simplification of pi by 3. There is the 1.6667. 1.6667. There is the simplification of pi by 3. Now, lambda t is equal to 2.303 log 1.667. Therefore, t is equal to 2.303 into, what is the value of log? 1.667. That is the 0.2218. Right? And this lambda is taken in denominator. This. But we know that lambda is equal to 0.693 upon tau half. Substitute here. Therefore, t is equal to 2.303 into 0.2218 into tau half upon 0.693. Clear? So, let us substitute the value of tau half here. So, we obtain 4223.49 here. That means the 4224 here. Approximate. Where is numerical? Here the question is quite lengthy, so we generally leave it. But actually, where is numerical? Here, the noble activity of the living carbon containing the matter is found to be 15 decays per minute. So there is the initial activity of a carbon specimen is given. Therefore, that is denoted by R0 is equal to 15 decay per minute. Right? Okay. For every gram of carbon, this activity arises from the small proportion of radioactive carbon C614 present with the stable carbon isotope C612. When the organism is dead, its interaction with the atmosphere causes and its activity begins to grow. From the known half-life 5730 here, there is the half-life of a given specimen. Therefore, the half-life is this 5730 years. And measured activity. The age of the specimen can be approximately estimated. We have to find out the given specimen is how much old. This is the principle of carbon C614 dating used in archaeology. Suppose a specimen from Mohenjo-daro gives an activity of 9 decay per minute. That means at present the activity of this specimen taken from the Mohenjo-daro is 9 decay per minute. So that is taken as only R. Right? Okay. Estimate the approximate age of Indus Valley civilization. That means we have to find out what are the specimen in Mohenjo-daro. Right? Is how much old. For that purpose, we know that the initial activity R0 is equal to lambda N0 and activity at present R is equal to lambda N. Taking the ratio of R to the R0, we obtain the N upon N0. But from the exponential law of radioactive disintegration, N is equal to N0 minus lambda T. Here we substitute the value of N. N0 cancel, only we obtain E2 minus lambda. Now, value of R and R0 are known. Therefore, E2 minus lambda T is equal to R is 9, R0 is 15. Now, here the negative power converted to positive. Therefore, take the inverse. E2 lambda T is equal to 15 by 9 is equal to 5 by 3. We are interested to find out the T. therefore taking ln, therefore lambda t ln E base E is equal to ln pi by 3. This value is 1. Therefore lambda t is equal to ln 1.6667. That is the simplification of pi by 3. Convert into log, therefore lambda t is equal to, we have to multiply the ln term by 2.303. Therefore 2.303 into log 1.6667. The value of the 1.667 is 0.2218. Take the lambda in this side, therefore in the denominator, therefore t is equal to 2.303 into 0.2218 upon lambda. But we know that lambda is equal to 0.693 upon tau half, because the tau half is given, not the lambda. Substitute here, as we substitute the value of tau half, we obtain the age of the specimen of Mohenjo-daro is 4,224 year old. Clear? Okay. Now the next is 13.9. Obtain the amount of cobalt 2760 necessary to provide the radioactive source of 8 millicurie strength. The half gram of cobalt 2760 is 5.3 kilo. So result activity is given. R is equal to 8 millicurie. That means the 8 into 10 is 2 minus 3 curie. But we know that 1 curie is equal to 3.7 into 10 is to 10 disintegration per second, or the decay per second. So it's equal to 8 into 10 is to minus 3. 1 curie is equal to 3.7 into 10 is to 10 decay per second. Therefore, the activity becomes 29.6 into 10 is to 7 decay per second. There is the result activity of cobalt. We require this activity of the cobalt. So how much amount of the cobalt is required? That means we have to find out the quantity of the cobalt which has the activity is 8 millicurie. Right? Okay. So activity is this. Tau half is also given. Okay? Half life is 5.3 year. 5.3 convert into second, therefore 5.3 into 3.16 into 10 is to 7 seconds. 1 year is equal to 3.6 into 10 is to 7. Therefore 16.748 into 10 is to 7 seconds. That is the tau half in second. Now we know that R is equal to lambda n. R is equal to lambda n. Lambda is 0.693 upon tau half. Right? Therefore, we require the n. N is equal to R by lambda. So it's equal to R upon 0.693 upon tau half. Therefore, R into tau half upon 0.693. Substitute the value, we obtain the value of n. Number of atoms required is n is equal to R value 29.6 into 10 is to 7. Tau half, already we know that 16.748 into 10 is to 7 divided by 0.693. 0.69. Thus we obtain the value is 7.1535 into 10 is to 16 atoms. Right? Okay. So that much atom is required in cobalt to get the activities 8 millicurie. Now listen, for cobalt 2760, the atomic mass is 60. Atomic mass is 60. Therefore, numbers of atoms in 60 gram of cobalt. Numbers of atoms in 60 gram cobalt. 2760 is, there is the NDS is equal to 60 into 8. Now 60 in already we obtained 7.15 into 10 is to 16. Thus we obtain 4.29 into 10 is to 18 atoms in cobalt of 60 gram required to obtain the activity of 8 millicurie. But we require the quantity of cobalt, not the number of atoms. Therefore, the required amount of source is m upon m is equal to NDS upon Avogadro number. Right? Because in one mole the number of atoms is equal to Avogadro number. So how much gram or how much quantity of the cobalt? Therefore, 4.29 into 10 is to 18 divided by 6.023 into 10 is to 23. So thus we obtain 7.123 into 10 is to minus 6 gram. So that much gram of cobalt is required to obtain the activity is 8 millicurie. Very easy, but there is a quite numerical like this way. First, what is given? Activity present given, convert into decay per second, right? After that, the tau half is given in here, also convert into second. Now, using the concept of equation of activity, I is equal to lambda in, find out the number of atoms. This number of atoms is required to get the activity 8 millicurie. But here, the specimen is given the cobalt, having the atomic mass is 60, right? Therefore, in 60 gram cobalt, how much number of atoms? First, we find out the NDS. NDS is equal to 60 into 9. After finding the number of atoms in cobalt 60, how much quantity of the cobalt is required? So this number of atoms divided by the Avogadro number. Thus we obtain the quantity of cobalt is 7.123 into 10 is to minus 6 gram. Clear? Now the next numerical is 13.10. The half-life of strontium 3890 is 20 years is given. What is the disintegration rate of 15 milligram of this isotope? Now listen here, the half-life of strontium is given. We have to find out the activity. For that purpose, first we have to find out in 90 gram strontium, the number of atoms is equal to the Avogadro number. We have to find out the activity of 15 milligram. Therefore, in 15 milligram strontium, how many numbers of the atoms are present? After finding the number of atoms in 15 milligram, we are using the equation I is equal to lambda n. We can find out the activity of 15 milligram of isotope of strontium. Right? For that purpose, what is given? Now, the half-life, now half is equal to 28 years. Convert into second. Therefore, 28 multiply with 3.16 into 10 is to 7 seconds. Therefore, we obtain 88.312. 88.312 into 10 is to 7 seconds. Right? Okay. Now the weight is given, m is equal to 15 milligram. Convert into the gram. therefore 0.015 gram. And atomic weight is given, capital N is given the 90 gram. So first way is to find out number of atoms in strontium of 15 milligram. For that purpose, in 90 grams strontium, numbers of atoms is equal to Avogadro number. Avogadro number is 6.023 into 10⁻23 atoms per gram. Atoms per mole. Right? Therefore, in 0.015 gram strontium, the numbers of atoms are N. We need to find out. N is equal to Ne into 0.015 upon 90. So substitute the value of Avogadro number 6.023, right? 6.023 into 10⁻23 into 0.015 upon 90. Thus we obtain the number of atoms 1.0038 into 10⁻23. Sorry, 20. These are the atoms in 15 milligram. Now, activity R is equal to lambda. Lambda is not given, instead of the lambda, tau half is given, therefore 0.693 upon tau half into N. Substitute the value 0.693. N is this 1.0038 into 10⁻20 upon tau half. Tau half is this 88.312 into 10⁻7. So thus we obtain the activity R is equal to 7.877 into 10⁻10 decay per second. Decay per second, or the disintegration per second. But we know that 1 QE is equal to 3.7 into 10⁻10. Therefore, activity in QE 7.877 into 10⁻10. Right? Divided by 3.7 into 10⁻10. Thus, there is the 2.13 Q. There is the activity. So, where is numerical? Here, the half-life of strontium is given the 28 year. What is the disintegration rate? That means we need to find out the activity of 15 milligram of strontium. For that purpose, the half-life is given, and also the quantity or the amount of strontium is given 15 milligram. First, we need to find out the number of atoms present in 15 milligram. For that purpose, in 90 gram, 90 is the atomic mass of the strontium. That means there is the mass of 1 mole of strontium. In 1 mole strontium, that means in 90 gram strontium, the number of atoms is equal to Avogadro number. Avogadro number is 6.023 into 10⁻23. Clear? Okay. Now, in 90 gram strontium, there are the number of atoms equal to the Avogadro number. Therefore, in 15 milligram strontium, number of atoms N is equal to 1. First, we find out the N by substituting the Na into 0.015 for 90. Thus, we obtain the number of atoms in 15 milligram strontium is this. We have to find out the activity of 15 milligram strontium. Therefore, R is equal to lambda N. Lambda decay constant is not given, but tau half is given. Therefore, relation of decay constant with the tau half is 0.693 upon tau half into this N. Here we substitute the value we obtain the activity is 7.877 into 10 is to 10 decay per second. That is the activity. Now, activity in QE, we know that 3.7 into 10 is to 10 decay per second is equal to 1 QE. Therefore, this activity in decay per second divided by 3.7 into 10 is to 10. Therefore, we obtain 2.13 QE. That is the activity of 15 milligram stone cell. Okay. Now the next is obtain the approximately the ratio of the nuclear radii of gold isotope Au 79, 197 and silver isotope Az 47, 107. Now we know that for gold, atomic mass number A1 is equal to 197, and for silver, the atomic mass number A2 is 147. Sorry, 107. 107. Now listen, that is the atomic mass number. For us, that is the gold 197. For silver, 107. Now we know that the radius of the nucleus R is equal to R0 raised to 1/3. We require the ratio of the radius. Therefore, R is equal to R0 raised to 1/3. Therefore, R proportional to the raised to 1. Now, the radius of the gold nucleus is I1, radius of the silver nucleus is I2. I1 upon I2 is equal to A1 upon A2 raised to 1/3. A1 upon A2 raised to 1/3. Substitute the value of A1 and A2. A1 197 upon 107 raised to 1/3. Now the simplification of 197 upon 107 is 1.8411 raised to 1/3. Okay, how we find out the cube root of this quantity 1.8411? For that purpose, we have to take the log on both sides. Therefore, log I1 upon I2 is equal to 1/3 log of 1.8411. 841. Therefore, there is the 1/3. Log of this quantity is 0.26550. Divided by 3, we obtain the 0.0883. That is equal to log of R1 upon R2. Taking the anti-log on both sides. Taking anti-log. Therefore, left hand side is I1 upon R2 is equal to anti-log of this. That is the 1.226. So this is the ratio of radii of gold to the silver. Okay. Now the mass density is independent of the radius. Therefore, the mass density of gold to the silver is 1. That is the answer. But mass density is independent of radii or the radius. Therefore, mass density of gold to the mass density of silver is 1. Again, we have to find out the ratio of radii, nuclear radius of gold to the silver. For the gold, atomic mass number is 197. For silver, atomic mass number is 107. We know the equation of nuclear radius R is equal to R0 a is to 1/3. R0 is constant. Therefore, R is directly proportional to the cube root of atomic mass number. That means the R proportional to a is to 1/3. Taking the ratio of radius of the gold to the silver, I1 upon I2 is equal to A1 upon A2 is to 1/3. Substitute the value 197 upon 107 is to 1/3. Okay, how we take the cube root of this quantity of the bracket 197 upon 107? For that purpose, first the simplification of this ratio is 1.8411. For that purpose, taking the log on both sides, log I1 upon I is equal to 1/3 log of 1.8411. Now the log of 1.8411 is 0.2653 divided by 3, we obtain 0.0883. Okay, is equal to log I1 upon I2. We require the I1 upon I2, therefore taking antilog on both sides. Therefore I1 upon I2, antilog of this is 1.226. 1.226 is the ratio of radius, nuclear radius of gold to the silver. Now what should be the mass density of gold to the silver? Mass density is independent of the radius. Therefore, the mass density of gold to the silver is 1. Clear? After that, the 13.12 is not in our syllabus, that is cancelled. Now 13.13, the radionuclei carbon 11 decays according to the carbon C611 converted to the boron 511 plus positrон plus neutrino plus Q amount of the energy is tau half is equal to 20.3. The maximum energy of the emitted positron is 0.960 MeV. 0.960 MeV. Given the mass value, mass of the carbon C611 11.011.434 atomic mass unit and mass of the boron 511 11.00305 atomic mass unit. Calculate the Q and compare it with maximum of the positron emitted. Maximum energy of the positron emitted. Okay. For that purpose, first the carbon radionuclei is decayed like this thing, C6, 11, convert into the board, 11 plus positron plus neutrino plus Q amount of energy. Q amount of energy. Now the Q amount of energy is equal to mass of carbon C611 minus mass of boron 511 minus mass of positron into C2 into C2. Okay. Now we can add this equation in that form. Mass of the carbon 11 minus how many positron? 6. Therefore, the mass of the 6 electron is subtracted. 6 in. Right. Now here the mass of the boron 11. Here the number of proton is 5. Therefore minus plus 5 in. This due to this minus, there is the minus again. So minus plus 5. Here 2 positron. That means the minus in. Whole system. So here remaining is minus 1 time semi, second time semi, therefore 2 times. Mass of the carbon C11 minus mass of boron 11 minus twice of M whole system. Right? Okay. Now we substitute the masses. Therefore, mass of the carbon already we have 11.01143 11.0, 11, 4, 3, 4, minus mass of the board 11.00305 minus twice of mass of the position, minus twice of mass of position is 0. We can add here minus twice of 0.0005.5 into system. Then, okay. So thus we obtain the simplification of this is 0.001033 atomic mass unit into C square. That is the Q. Now we know that directly the energy released is multiplied with the atomic mass defect with the 931.5 MeV. So we can add 0.001033 with 931.5 MeV upon C square into C square. Therefore, C square cancel. That means atomic mass unit is 8. Okay. Therefore, 0.9622 MeV. That means the 0.96 MeV. Energy is released during this decay. Again, first we have to calculate the Q value. Q value of this equation, say carbon 611, boron 511 plus position plus neutrino plus Q amount of energy. So Q is equal to mass of carbon minus mass of boron minus mass of position plus neutrino is massless into C square. So as we substitute the value, here carbon has the 6 proton, therefore 6 electron mass, because the mass of the 6 proton is also subtracted. Now boron has the first proton, 5 proton, therefore 5 proton mass of the electron is subtracted. Therefore this negative becomes the positive and mass of the positive. So as we substitute the value of mass of the carbon, mass of the boron, and this simplification 6 Me plus 5 Me minus Me. That means the minus 2 Me is Me. So as we substitute this value, so that much atomic mass unit into C square. That is actually mass defect delta M into C square. Now we directly convert the delta M mass defect into energy by multiplying the 931.5 MeV per C square. So C square cancel, so that much Q value is obtained. Now we have to compare this Q value with maximum energy of positive energy. Now listen here. The mass of the boron is much more compared to the mass of the positive and neutrino. Mass of boron is much more than positive and neutrino. Then, so energy of boron is 0. Boron is 0. And kinetic energy of neutrino is minimum. Because since it has no mass, therefore Q is the energy of positive. Q is the energy of positive. Therefore, the kinetic energy of the maximum energy of positive is Q Q is equal to E plus is equal to 0.96 MeV. 0.96. This is the maximum value of maximum energy of positive.